And yeah, they break up all this non-covalent interaction, and the whole virus just falls apart like a house of cards.
Hi everyone. So we are trying to get more videos out to you, but right now our entire team is practicing social distancing and working from home. So that makes it kind of tricky making our normal videos. With that said, we still wanted to bring you some good information on the science of what's happening with COVID-19. So I found that everyone seems to be talking about soap and the importance of soap. And so I wondered, is it actually that effective against viruses, or this virus in particular? And if so, why? Those questions led me to a chemist in New South Wales who's an expert on the topic. His name's Pali Thordarson, and he's insanely busy right now. So I was fortunate that he took a bit of his time to talk with me.
It's been quite a media storm too. So I think I'm up to 3 radio interviews, 1 TV, and probably about half a dozen of these where we are doing. So.
All right. Well, thank you, Pali, for chatting with me. So actually, I found you initially by seeing a Twitter thread about why soap is so good at killing viruses. So first off, I guess we'll just get right into it. Why is soap so good at killing viruses?
Because it completely destabilizes all the non-covalent interactions that hold the virus together.
So when Dr. Thordarson says that hand soap destabilizes non-covalent interactions that hold viruses together, what he's saying is that the components of a virus are just not that tightly bound to each other. So with covalent bonding, for instance, the bonding that you would see between carbon atoms in a diamond, you have the sharing of electron pairs, and that makes for much stronger, stable bonds. But in the case of viruses, you have these non-covalent interactions. They're much weaker, and they include things like hydrogen bonding and van der Waals forces.
What you have is first an RNA cell samples with several protein units. The whole cluster is just held together by hydrophobic and charge and hydrogen bonding interactions between the protein units and the RNA. There's no covalent bonds linking all that stuff together. And then there's a bilayer lipid membrane around the whole thing with some protein sticking out.
So all viruses have a genetic component, whether that's DNA or RNA, and they also have proteins. Some also have lipids. Like Pali mentioned, they self-assemble into a new virus, and then that virus can go on to infect more of your cells. When viruses have lipids around the outside in what's called a lipid bilayer, those viruses are considered enveloped. So SARS-CoV-2 is enveloped, as are others like a bunch of the influenzas and hepatitis B. And that makes a difference for how they interact with soap.
In the case of the virus, it will stick to your hand, for instance, if you pick it up from somewhere. It's also a little bit greasy. And that's, again, I think you can readily see as a chemist because the surface of the skin is not that dissimilar. It's a mixture of proteins and fat from the dead cells on top of your on top of the skin. So you get a fairly good adhesion there. So when you just run water over the hand, the virus may not come off. It might, but it might not, right? When you add soap water, what happens there, of course, is that now we got a solution full of amphiphilic molecules, whether they are synthetic or natural, doesn't really matter. And those start to exchange with the membrane, they stick into the membrane, and when that happens, the membrane obviously would become less stable. And yeah, they break up all this non-covalent interaction, and the whole virus just falls apart like a house of cards. So that's why the soap works so much better than running water.
Here's what that looks like. Hand soap is made up of molecules called surfactants. Surfactants have a hydrophilic or water-loving end and a lipophilic end that likes lipids like those in the lipid bilayer of enveloped viruses like SARS-CoV-2. So these surfactants can actually wedge their way into the lipid bilayer, lipophilic end first, and when they do, the virus will break apart. Surfactant molecules will come in and surround those broken down viral components. And as you're washing your hands, water will come in, hydrophilic ends of the surfactants will interact with it, and the virus will get washed away. So I've actually been riding the metro in Washington, D.C., and I think starting today I'm going to stop doing that, and I will be switching to some remote work. But, you know, I have my hand sanitizer in my bag. I use it right when I get off the metro, walk the 4 blocks to work, and then immediately go into the bathroom and wash my hands with soap and water. So
excellent. And I think we need to remember, too, people that we are, by doing that, what are you doing? You are also helping the entire society. sooner or later you might be unlucky and you might get sick, but just what you've done now has also slowed down the spread.
Yeah.
And that might have saved other people, because you all heard about the curve now. We need to try to keep the epidemic down a little bit longer so we don't overwhelm the hospitals.
So we're going to keep trying to bring you these shorter videos while we're quarantining. In the meantime, keep washing your hands with soap and water. The CDC recommends spending at least 20 seconds doing so. And most importantly, try to limit your contact with other people. The more that we're around others, the more this virus has a chance to spread. So stay safe and stay home if you can.